Good morning. It's February already. I'm back from my hiatus. I was so burned out doing all those SAT problems, but now I am ready, and I will start doing some physics. So we've done a bunch of projectile motion, what happens when you throw something in the air or drop it from a cliff. But now what I want to introduce you to is how do you actually affect the acceleration of an object. And to do that, I'm going to introduce you to Newton's three laws. Newton's three laws. And this is kind of, to some degree, what we were doing before was derivative of what I'm going to do now. But this is kind of the backbone of classical physics. So Newton's three laws. And you've probably heard of these before. Newton's three laws. Or sometimes I call them Newton's laws of motion. Or I've actually looked this up on the web just to make sure to see if there was any correct way of writing it. But every website seems to have a different paraphrase of the laws. But hopefully I can give you an intuitive sense of what they are. So the first law is an object at rest. An object at rest tends to stay at rest. Stay at rest. And an object in motion tends to stay in motion. This is what I learned when I was a kid, and now when I look at Wikipedia and things, there are some paraphrases, and we'll go over those paraphrases because I think they're instructive. Stay in motion. And you might say, Sal, this is obvious. Why does Newton get so much credit for stating the obvious? Obviously, if I look at my sofa, for example, it is an object at rest, and if I keep staring at it, it tends to stay at rest. Likewise, when I look at a car crossing an intersection, that's not a red light, that's crossing an intersection, it's an object in motion. And then, I don't know, 10 seconds later, it's still staying in motion, and of course it'll stay in motion unless you press the brakes or whatever. So you might say, well, Sal, this is the most obvious thing ever. This doesn't even need to be written down. But let's say you were Newton and you came to me, and sometime was in the 17th century, and you said, Sal, I have these new laws, and the first is an object at rest tends to stay at rest, and an object in motion tends to stay in motion. And I'll say, Newton, I can already disprove your law. Let's say I have an apple, and I'm holding it up at, let's say, I'm holding it up with my arm, so it's roughly, my shoulder level. So I'm holding an apple. This is an apple. Looks like a heart, but it's an apple. So I'm holding it with my hand. I'm drawing my hand. I don't know if that makes sense to you, but I'm holding it with my hand. And what happens when I let go of that apple? So while I'm holding it with my hand, it's an object at rest, right? But then when I let go, what happens? It falls, right? Falls to the ground. So I'll say, Newton, I just disproved your first law because this was an object at rest, and I did nothing to it. I just let go. I didn't apply, I didn't push it, I didn't pull it, I didn't throw it, I didn't do anything. And when I let go, it just fell to the ground. It started moving without me doing anything, even though it was an object at rest. And then Newton will say, oh, well, that's because, there's this thing called gravity, and it's the force of gravity. And I would say, Newton, you need to start to learn to not make up things. Just because your law doesn't make sense, you don't need to make up artificial forces in the universe. But anyway, he would end up being right. And the way to think about this, if I did this exact same experiment while I was in space, and let's just say, I was going to say orbit because it would look like that, but even orbit is kind of you're still kind of falling towards the Earth. It's just you're moving. Well, I won't go into that. I'll go into orbit at another time. But let's say we were just in deep space, and me and the apple were just floating around in space. And we don't even know. Maybe we're stationary. It's hard to say. We're floating with respect to what. And then if we're in space and I let go of this apple, what happens to the apple? Nothing. It's not going to fall anywhere. It's not going to move. And so whenever you think about Newton's laws, and that's why this is so amazing. He didn't know about space. He's living in this planet that, everything tends to fall and things start moving for no reason because of whatever gravity and the wind and whatever else. And he actually theorized that there could be a place where there's no forces acting on objects, where if I were to let go of this apple, it would just stay where it is. And similarly, the object in motion tends to stay in motion. And there again, I would have told Newton, well, that doesn't make sense. If I were to push a, well, I don't know if they had bowling balls back then, but if I were to roll a bowling ball down a, well, let's say up a hill, right? At some point, that bowling ball is going to slow down, right? If if I rolled it up a hill, at some point it's just going to slow down, and maybe if I got it right, it would just stop at the top if I did it perfectly, right? And I could say, look, this was an object in motion. At some point it stops, or it actually turns back around. Or even if I were to roll it this way, at some point it's just going to stop, right? The bowling ball is going to stop. Or another way, I could, if I were to push something as hard as I could, maybe it travels for a couple of feet, but then it's going to stop. And he'll say, oh, well, you know, there are these forces that you're not realizing. There's the wind resistance in the bowling ball example. There's the force of friction in the example where I just push something, and I would have said, well, Newton, you're just making up these forces again. And this is why this is so not intuitive, because he had to essentially realize that there were all of these forces acting on something, when to someone at that time, you wouldn't have realized it, and you wouldn't have been able to even conceive that there's a place called, space, for example, where these things wouldn't happen. If I push something in space, it will keep going. It would be an object in motion, and it will keep that velocity until some other force acts on it. So it wasn't that intuitive. And so a more modern way to write this is to say that there is a frame of reference. There exists a frame of reference, and I'll explain what a frame of reference is. But there exists a frame of reference where this is true. That could be the new way of saying Newton's first law of motion. So what's a frame of reference? That is, so everything in physics, if I'm moving relative to what? Relative to the observer, moving relative to the earth, you don't know. So a frame of reference is, what is the observer doing? So example, when I'm in space and I let go of the apple, me and the apple are kind of in this, I am observing the apple from what I call an inertial frame of reference. So this is a frame of reference actually where Newton's laws hold. If I take the apple on Earth and I let go and it drops, the reason why this first law didn't hold is because I'm not really in an inertial frame of reference. Because me and the apple are both constantly being pulled on by this force called gravity. So although it looks like, nothing's going on, me and the apple are in the same, nothing's really acting on us, there's this force of acceleration. Similarly, if I'm in a car and that car is accelerating, right? So, let's say the car looks more like a pickup truck, so I'll go with the pickup truck. So we've all, and you have that little thing, let's say you have a pair of dice hanging from your rear view mirror, right? This is the dice right here. What happens when the car accelerates? Well, the dice move back, right? And so when you're sitting in the truck itself, it looks like the dice are just moving back. No one's really doing anything to it, but especially, let's say the car had no windows, and you would just all of a sudden mysteriously feel, well, you would feel a little squeezing on your chest too, but you would also just see these dice move back, and you'd say, hey, this Newton's first law doesn't hold. And what I would say, well, that's because you're in a non-inertial frame of reference. To someone outside of the truck, they would see, oh, well, the truck is moving, the truck is actually accelerating, and that's why the dice moved back. So in I guess you could say the horizontal dimension, and I'm probably just confusing you, but I want to give you a really intuitive feel about why this isn't so intuitive. In the horizontal direction, because there are no forces of gravity or whatever acting in this direction, and if I'm outside of the truck, I would be in an inertial frame of reference in at least the horizontal dimension. I mean, we always have gravity pulling down on us, but from the outside of the truck, I could observe that, oh, Newton's law holds because the whole frame of reference, this truck is actually being accelerated. So me being outside of that, I would be in an inertial frame of reference. Hopefully I haven't confused you too much. The way to think about it is an inertial frame of reference is just a frame of reference where there's no outside forces acting on the whole frame of reference. And a frame of reference is just what is the observer doing? What am I doing? Am I moving with the object? Am I being accelerated with the object? Or are neither me nor the object being acted upon? And that's the way to think about it. I already ran out of time. I only got one law done. So I'll see you in the next